Yeah, okay, class. In the last class, I think the functional groups are completed. What is the carboxylic acid, aldehyde, ketone, and something like that, right? Now, before going to another concept, just I am giving one question on the basis of what functional groups. Now, this one also very important, right? Now, here our question is identify number of functional groups in the given compound. This is the question. Identify number of functional number of functional groups present in the given compounds. Okay, that is our question. Yes, you write same thing. Identify number of functional groups present in the given compound. Okay, yes, everything is connected, fine, right. Now this is our compound. Here some 6-member ring system is given, right? Yes, here one functional group is given like this, C double bond O. Next one, C double bond OH. Next one here, Cn. Somewhere it is connected like this, NC. Next here some OH is given, okay. And here some aromatic ring system is given, and here they are connecting OH. This is the first molecule, right? Just identify number of functional groups present in the given compound, okay. How many number of functional groups present in the given compound? So very simple, already we have very good idea about the all types of functional groups, right? So based on that, identify number of functional groups present in the given compound, right? First I am starting from here, carboxylic acid. What is the name of COOH? Carboxylic acid. And C double bond OH, what is the name of that functional group? Aldehyde. So whatever the type of question they can give, like how many types of functional groups present in the given compound, that is one type of question, okay. And which of the following functional groups are present in the given compound, or which of the following functional groups are not present in the given compound? So any type of question, right? Yes, carboxylic acid and aldehyde is completed, and here Cn is given, right? Cn cyanide. One second, I want to change this. Okay, no problem. Nc is given, no need to change. Cn cyanide, and here which is directly connected to the ring system or carbon, here nitrogen is connected, okay. Nitrogen connected, this one is taken as Nc, or just in order to avoid confusion I am writing like this. Yes, N. Okay, one second. Yes, Nc, that is not Cn, that is Nc, okay, isocyanate, right? That is also our different functional group. Yes, and we know that simple OH, but here OH is connected to the ring system, aromatic ring system, okay. These are the functional groups. Totally how many functional groups present in the given compound? So what is our answer? 1 2 3 4 5 6. Now that is the answer, okay, right. Yeah, it is visible, no problem. Now come to next question. I am going to give another question. Yes. Now you start a compound like this, COOH, and here something like OH is connected, okay, and here some Cn also present, and here C double bond O N, C double bond O N H, C double bond O N H, and further this one connected to some aromatic ring system, okay. Here something like OH group is given, and further they are connecting like this, NH, and again here NH2. Identify total number of functional groups present in the given compound, okay. Very good question, right? First let us start from carboxylic acid. Yes, this is our functional group. Clear? Next one, OH is the second functional group, like that. Cn is the third functional group, and here which is present? Yeah, C double bond O N, acidamide functional group is there. And what is the degree? Now here 2 degree acidamide is given, okay, 2 degree acidamide. And next this one also considered as one functional group. Why? Because OH directly connected to the aromatic ring system. Okay, right. And here what is the type of amine? Now this is 1 degree, 2 degree or 3 degree. Now this one 2 degree amine, clear, and here 1 degree amine. So 1 degree amine and 2 degree amines are same functional groups or different functional groups. Already we know that 1 degree, 2 degree, 3 degree amines are different functional groups. 1 degree, 2 degree and 3 degree amides are different functional groups. That's why don't get confusion, right? Here one is secondary amine and one is primary amine. 1 degree amine and 2 degree amine, these are considered as different functional groups. Clear? Then what are the total number of functional groups present in the given compound? 1, 2, 3, 4, 5, 6, 7. So our answer is 7. These are the total number of functional groups present in the given compound. Okay, right. Next one, I am going to give last example in the identification of functional groups. Okay, right. Here I am keeping double bond. Next one here something like aromatic ring system given. Here I am taking OH, and further here now something like OH is given. Okay. Next one, here C double bond O. Next one C double bond O something, right, and here C double bond O R. Next in the further connectivity there is a NH and further connectivity is like this. Okay, next one here we are taking NH2 NH2. Next C double bond O here. Once again here you write like this, C double bond OH carboxylic acid. Next in last one I am taking like this, C double bond O. One second, just in order to avoid confusion, here O C double bond O H. This is our compound. From that identify total number of functional groups. So whatever the lengthy molecule they are giving, that is not a what problem, but only thing is you are in a position to identify types of functional groups present in the given compound, right? Yeah. So where from we are going to start? Yes, double bond also considered as one functional group. For example, in any given compound, if there is a double bond as well as triple bond, both are considered as different functional groups. Okay, right? So our double bond is one functional group. Next one we can take it as functional group. Yes, OH also one functional group. And here what is the name of this? COOH. It is acid. It is carboxylic acid. Okay, right? Next one, you look at this functional group. What is the name of this functional group? That should be taken as what? Anhydride. Is it clear? Yes, anhydride, acid anhydride. Okay. Next one, what is the name of this particular segment? This particular segment is taken as ester, and it is what type of amine? Yes, secondary amine. That is also considered as one functional group. And here primary amine is present. That primary amine, 1 degree amine, also considered as one functional group. Okay. And what about last one? Sometimes now students are getting little bit confusion here, right? Now this carboxylic acid and this one slightly they are what looking like same but not exact. Just you carefully observe this one. What is the name of this particular segment? What is the name of this segment? Whether it is carboxylic acid or ester. Now this is the ester linkage. Which one is considered as carboxylic acid? C double bond OH. Now this segment is taken as carboxylic acid. Already here carboxylic acid is present. Now this is the carboxylic acid. But this one carboxylic acid or ester. Now this functional group is taken as ester. Okay, right. Then we consider totally how many different types of functional groups. Here already ester is present. This particular segment is ester. Here also ester. That's why we consider only one. Yeah, okay. One second. Yeah, this one also ester. But if you want to write total number of functional groups, yeah, you start from here 1, next 2, next 3, and here 4, and what about this one? 5, ester 6, secondary amine 7, primary amine 8. Now is it considered? No. Why? Because already ester is there. Ester again ester. They are not the different functional groups. ester functional group only. Okay, that's why we consider only one time. So that's why what is our answer? Total 8. Okay, right. 1, 2, 3, 4, 5, 6, 7, 8. That is our answer. That is the way of identification of functional groups. Okay, clear. Next one. After completing identification of functional groups, now we are going for homologous series. That is also very important. Homologous series. Homologous series. What is the meaning of homologous series? Here nearly 4 to 5 very important points are there. All these points are okay, easy to understand. First, let me take one simple example that I am taking carboxylic acid like HCOOH. Any functional group you can use, no problem. But just for understanding purpose, I am starting with carboxylic acid HCOOH. What is common name of that acid? Formic acid. But here we don't want any common names, IUPAC, not like that. Just we are trying to understand, right? What about the homologous series? Yes, HCOOH. And same thing here I am writing like this H, but in between these two I am taking extra CH2. Yeah, COOH. Next one, I am going to take one extra CH2 like this CH2, CH2, COOH. Now let us take one more molecule just by increasing CH2 again COOH. Let it is first molecule, second molecule, third molecule and fourth molecule. Just I am taking 4 molecules, sufficient, right? Now, how do we understand homologous series? First, you observe this one. For example, here all are carboxylic acids. Okay, all are carboxylic acids. General formula of all these carboxylic acids same or different. Now, first I am going to write. What about the general formula? Simply I am writing like this: GF. GF nothing but general formula. Okay, right. General formula same or different? Yes. General formula same. And second one, functional group same or different? Same functional group. Same functional group. Same functional group. Okay. Yeah. And what about third one? If functional group is same, then chemical properties same or different? Yeah, definitely chemical properties are same. Now here same chemical properties. Same chemical properties. Clear? All these points are very important. Only on the basis of molecular weight difference 14, then those are known as homologous series. That is not the correct statement. Why? Because nearly 4 to 5 important points are there. And what is the first one? General formula same general formula. Second one, same functional group. If your functional group is same, then what about the chemical properties? Chemical properties are also same. Now, if you observe 1, 2, 3, 4 molecules, so what about the molecular weight? Yes, molecular formula exactly, sorry, a general formula is same. But molecular weight changing or not? From first compound to second compound, there is a change in molecular weight. 2 to 3, again change in molecular weight. 3 to 4, again change in molecular weight. That means molecular weight same or different? Different molecular weight. For example, if you are changing molecular weight, even the same functional group, for example, if you concentrate about chemical and physical properties, because of the presence of same functional group, chemical properties same or different? No problem, chemical properties are same. But what about the physical properties? If you are changing the molecular weight, your physical properties are affected. Physical properties are not same. Okay, right. I am writing here fourth point. They are having different physical properties. Different physical properties. Different physical properties. Different physical properties, right? General formula same and same functional group, same chemical properties. And what about physical properties? They are having different physical properties. Okay, right. So whenever these conditions are satisfied, then your molecules are said to be homologous series. But here one more important condition is there. Now in case of homologous series, okay, no problem. For example, if they are asking like this, what is the molecular weight difference between these two, HCOOH and HCH2COOH? What is the molecular weight difference, or what is the difference between these two? CH2 is the difference. What is the molecular weight of CH2? Now 14. Now 14 mass difference is there. Again between these two, what is the mass difference? 14. Again between these two, mass difference is 14. Now if you compare homologous series, last important condition, yes, general formula same functional group, same chemical properties and different physical properties, but at the end of this homologous series, what is the last and very important point? Whenever you are comparing now homologous series, always you should compare adjacent molecules but not non-adjacent molecules. For example, in order to explain homologous series, yes, you can select 1 and 2, no problem. Why? Because they are adjacent molecules. And you can select 2 and 3, yeah, no problem. You can select 3 and 4, no problem. Okay, always for homologous series, now you should select adjacent groups, adjacent molecules only, 1 2 2 3 3 4 4 5, like that. But for example, 1 and 3 is given, they are not adjacent. Next 1 and 4 is given, they are not adjacent. 2 and 4 is given, they are not adjacent. Okay, that is very important condition. So last point I am going to write same thing, molecules. Last point, molecules molecules should be molecules should be adjacent to each other, adjacent to each other. All these 5 points are very important. If any one of these conditions are not satisfied, then that is not the homologous series. Okay, right. Why we are not going to write CH2, that I will tell you. For example, here the question is given like this: which of the following is homologous series? Yes, 1 2 homologous, 2 3 homologous, 3 and 4 also homologous. For example, question is given like this, by giving these two HCOOH and CH3COOH, acetic acid molecule. These are the homologous series and these are differentiated by mass difference 14. Yes, correct. But that is not universal, that is not applicable for all molecules. Okay, sometimes other than 14 difference or 14 difference is also observed. In that case, CH2 or mass difference 14 is not the universal statement. Okay, so once again, before closing this homologous series, now I am going to tell that what is the general formula. Same general formula, functional group same chemical properties, different physical properties. Molecules should be adjacent to each other. Very important point. Molecules should be adjacent to each other. But sometimes but not every time, sometimes homologous series, now mass difference is 14, only sometimes but not everywhere. Okay, right. Now you look at this example. Now CF4 molecule, 4 fluorine atoms present on the carbon atom, right? And second molecule I am taking like this: fluorine, 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 again fluorine. These two are also homologous to each other. But what is the molecular weight difference? 14? No. There is no mass difference 14. That's why that is not the universal statement. So once again, I am going to repeat the same point. In any particular molecules, like formic acid is given, acetic acid is given, these two are what said to be homologous. What is the mass difference? 14. No problem. But everywhere that mass difference 14 we are not applying. This is the best example. Okay. So this is the story about homologous series. Yeah. Come to next concept. Here question is given like this. Yes, 3 carbon atoms are there with NH2. For example, by changing mass difference, if you are going to write like this, NH and CH3, what is the mass difference between these two? Otherwise, clearly I am writing like this. Yes, it is CH3. Next one, CH2, CH2, NH2. First one. Okay. Next one, CH3, CH2. Again, CH2. Here, NH and CH3. What is the difference between these two molecules? What is the mass difference between these two? Yes, 14 is the mass difference. But these are not the homologous series. Why? Because What is one of the important condition here? What is the degree of amine? Primary amine. Okay, and what is the degree of amine? Here it is secondary amine. Is it clear? Yeah, one is primary amine and one is secondary amine. So these two are same functional groups or different functional groups. These two are what? Different functional groups. Once different functional groups are given, even though mass difference 14, they are not the homologous series. Very important point. So to take homologous series, we should maintain same general formula, same functional group, same chemical properties. Molecules should be adjacent to each other. Okay, that is a story about homologous series. Next one more important point. Sometimes they are giving question on OH groups. That is also very important. Here I am taking like this. Okay, OH, right? And second molecule like this, CH2OH. You look at these two. What is the mass difference? Yes, mass difference is 14. Why? Because this is the difference between these two molecules. Why? Because if you have any confusion, you can also write like this. The given molecule benzyl alcohol CH2OH. What is the difference between these two? Only CH2. Okay. And what is the mass of that CH2? Yes, 14, not minus 14. Don't get confusion. This is only 14. Yeah, 14 is the mass difference. But these two are not the homologous series. Why? Because here OH directly connected to the aromatic ring system. But here OH directly not connected to the aromatic ring system. Now these two are same functional groups or different functional groups. These two are considered as different functional groups. If different functional groups are what given, even though mass difference 14, they are not homologous series. That is a very important point. That's why now mainly about mass difference 14. Now you concentrate. Just mass difference 14 is not sufficient condition for homologous series. You should be with the same molecular formula, same general formula. Next one, functional group also same, and molecules should be adjacent to each other like that. So these are the conditions for homologous series. Now just you tell me this last point. These two are homologous series or not? These two are separated by mass difference 14, but still they are not homologous series. What is the reason? Different functional groups. Okay, clear. For example, if this is the given molecule, CH2OH is given. In the second molecule, CH2OH is given. These two are homologous series or not? Yes, these two are homologous series. Why? Because here OH is not directly connected to the ring system. Here also same thing, right? These two are what? Adjacent molecules. All conditions they are satisfying. So your molecules are said to be homologous series. These two are homologous series, but these two molecules are not homologous series. Why? Because they are considered as different functional groups. Clear? Yeah. Next concept, calculate or identify hybridization in the different compounds. We know that, for example, around any atom, two sigma bonds are present. What is the hybridization? sp. Actually, we are considering hybrid orbitals, sigma bonds and lone pair of electrons. But there is a very vast topic in chemical bonding. There we will discuss very clearly. But here, just to remember this point, if you have two sigma bonds, if you have two sigma bonds, what is the hybridization? sp. And if you have three sigma bonds, sp to hybridization, and four sigma bonds, sp3 hybridization. Okay, right. On the basis of that, just you practice some examples. These are also very important for mains. Yeah, first I am going to give very simple example. I am taking ethane molecule. What type of questions now they are giving from this concept of hybridization? Yes, ethane molecule is given, very simple molecule. First I am giving, our first question is total number of hybrid hybrid orbitals. That is our first question. Okay, clear. Next one, total number of pure p orbitals. That is the second question. Third one, total number of pure s orbitals, s orbitals. That is the third question. Fourth one. So they are generalizing like this. Total number of pure orbitals. Total number of pure orbitals. Okay. Total number of pure orbitals nothing but combine both p and s orbitals. Orbitals. Yeah. Total number of pure orbitals. For example, particularly if they are separating like what are the total number of pure s orbitals and pure orbitals like that. Now individually you calculate, and if simply they are giving like this, what are the total number of pure orbitals, you combine both s and p orbitals. Okay, right. And we know that sigma bonds are formed by hybrid orbitals and pi bonds are formed by overlapping of pure atomic orbitals. Okay, pi bonds we are not getting from hybrid orbitals. Yes. Now you start from this molecule here, carbon and carbon. What is the hybridization of carbon? Around the carbon atom, how many sigma bonds present? 4 sigma bonds are there. Then what is the hybridization of this carbon atom? Yes, sp3 hybridization. And what is hybridization of this carbon atom? Once again sp3 hybridization. These two carbon atoms undergoing sp3 hybridization. Clear? That means for first question, what is the answer? Total number of hybrid orbitals. Total how many hybrid orbitals are there? In sp3 hybridization, 1s, and how many p present? P, P, P. 3 p's nothing but px, py and pz. Okay. And again in sp3 hybridization here we have s, p and p. P, P, P nothing but p orbitals are there. 3. How many p orbitals present here? 3 p orbitals are there. Okay. 3 p orbitals. Something lagging is there. Okay, no problem. sp3 and sp3, spp, spp, right? Total how many hybrid orbitals here? Yes, our answer is 8. These are the total number of hybrid orbitals. Next question. Total number of pure p orbitals. What are the total number of pure p orbitals? 0. Why? Because for example, in case of 1 s orbital and 3 p orbitals, for example, if these two orbitals participating in hybridization, then what is your hybridization? sp. Then how many pure p orbitals left? 2. For example, if 1s 2 p orbitals are participating, then what is your hybridization? sp2. How many pure p orbitals left? Only 1. For example, spp. Hybridization sp3. How many pure p orbitals? 0. That's why there is no pi bond. Okay. Yes, here number of pure p orbitals equals to 0. Total number of pure s orbitals. So where from we are taking s orbitals? Now, which color is better? Okay, right. Total number of pure s orbitals. We are selecting from hydrogen. Now hybridization, carbon undergoing hybridization. Okay, and here hydrogen providing s orbital, pure s orbital for the molecule formation. S orbital, s orbital, yes, yes, and yes. How many number of pure s orbitals are there? Number of pure s orbitals equals to 6. And for example, last question, total number of pure orbitals. 0 plus 6 equals to 6. That is the way in identification of hybrid orbitals. Next one, pure orbitals, pure p orbitals, pure s orbitals are total number of pure p orbitals. Okay, right. Come to the next question. Let us take one unsaturated system. Yes, this is my unsaturated system. Double bond, again single bond. Yes, here something like double bond is given. First question, total how many number of hybrid orbitals present? Yeah, what is hybridization of this carbon? Actually, according to the carbon valency, if question is given like this, okay, here how many hydrogen atoms are left? Yes, to satisfy carbon valency, we are taking 2 hydrogen atoms. Here already how many bonds are there? 3 bonds are there. Extra we require 1 bond. Here already 2 bonds are there. Remaining 2 are satisfied by hydrogen atoms. Clear? And here 1 hydrogen, hydrogen and hydrogen. That is the way of taking hydrogen atoms. Okay, right. Yeah, come to next one. What is hybridization of your carbon atom? What is hybridization of this carbon atom? sp2. I think it is not visible. One second. Better to take yellow color. Yeah. Here it is sp2 hybridization. Next sp2 hybridization. Here sp3 hybridization. Next sp2 hybridization. Again sp2 hybridization. Now you calculate total number of hybrid orbitals. Now here total number of hybrid orbitals. What are the total number of hybrid orbitals? What is the answer for total number of hybrid orbitals? sp2. How many orbitals are there? 3. One s orbital, next two p orbitals. Yeah. From here 3. Clearly I am writing like this. sp2 hybridization. Again sp2 hybridization. Next sp3, sp2, again sp2 hybridization. From here 3, 3, 4, 3 and 3. Count total number of hybrid orbitals. Yeah, 3 plus 3, 6, 6 plus 4, 10, 10 plus 3, 13, 13 plus 3, 13 plus 3, 16. Yeah, that is the answer. 6 plus 4, 10, 10 plus 3, 13, 13 plus 3, 16. Total number of hybrid orbitals. Yeah, next you calculate total number of pure orbitals. That means p plus s orbitals. Now in case of sp2 hybridization, how many p orbitals left? One p orbital is left. Yeah, we can take like this. One p orbital is left plus. Next one here, one p orbital is left. Is there any pure p orbital here? No, all p orbitals participating in hybridization. Next sp2 and sp2. Yes, p plus p. These are the pure p orbitals. They can give question either in terms of total number of pure p orbitals or total number of pure s orbitals or simple total number of pure orbitals. Total number of pure orbitals nothing but sum of p orbitals and s orbitals. Yeah, first I am taking p, and where from we are selecting s orbitals? Hydrogen 1, 2, 3, 4, 5, 6, 7 and 8. Total 8 s orbitals. Okay, 8 plus 4, 12 pure p orbitals. Sorry, total pure orbitals. Combination of p and s. How many pure p orbitals present? 4 pure p orbitals. How many pure s orbitals present? 8 pure s orbitals present. These s orbitals we are taking from hydrogen, and what is the final answer? 12. Total number of pure orbitals. Okay, right. Yeah, clear. Come to next question. Just I am giving benzene molecule. Any type of molecule given, same method. Okay. Yeah, benzene molecule. Yes, very clear. Pi bond, pi bond, pi bond. Just they are giving molecule like this. And first arrange hydrogen atoms. Okay. How to arrange hydrogen atoms? Yes, here we can take hydrogen, 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 and last hydrogen. Okay, right. That is our benzene molecule. First you find out total number of hybrid orbitals. What is hybridization of each carbon atom? Yes, it is sp2. Here also same sp2. Yeah, sp2 fine. And this one sp2 carbon, sp2 carbon, sp2 carbon and sp2 carbon. Why that is sp2 carbon? You select any carbon atom. For example, you select this carbon atom. What is nature of this bond? Nature of this bond. It is sigma bond or pi bond? Yes, it is sigma bond. Sigma bond. Next one, around the same carbon atom here. What is nature of this bond? Sigma bond. Again, around this carbon atom, sigma bond is there. Like that, around each carbon atom, how many sigma bonds present? 3 sigma bonds are there. Sigma bonds are formed by hybrid orbitals or pure orbitals? Hybrid orbitals. Okay, that's why sp2 hybridization. Now totally how many sp2 present? We have 6 sp2 hybrid are 6 carbon atoms with sp2 hybridization. From sp2 how many orbitals? 3. Again here 3, 3, 3, 3 and 3. Total 6. 6 into 3 equals to 18. These are the total number of hybrid orbitals. Total number of hybrid total number of hybrid orbitals equals to 18. Very important question. Total number of hybrid orbitals equals to 18. Total number of hybrid orbitals equals to 18. What is our next question? Total number of pure p orbitals. Let me remove this one. Our first question is completed once again. If they are giving molecule like this and they are asking what are the total number of hybrid orbitals. Okay. To calculate the total number of hybrid orbitals, first you try to identify hybridization of each carbon atom. From that you will get idea. What are the total number of hybrid orbitals? 18. Next question, how many pure p orbitals are there? Here I am going to take pure p orbitals. In sp2 hybridization of each carbon atom, how many pure p orbitals left? Pure p orbitals from each carbon atom. Here one p is available. sp2 here also one is available. P, P, P and P. Total how many pure p orbitals? 6 pure p orbitals are there. And what about total number of pure s orbitals? From each hydrogen atom we are selecting now one pure s orbital. Total how many pure s orbitals? 6. So once again I am writing like this in benzene molecule. In benzene molecule, okay. In benzene molecule, first point, total number of in benzene molecule, total number of hybrid orbitals equals to how many? 18. Next one, second important point. What is the second important point? Total number of pure p orbitals equals to how many? 6. Next one, total number of pure s orbitals equals to 6. That is the question. For example, if question given like this, what is the between ratio between hybrid orbitals and pure orbitals? Pure orbitals given, they are not giving particular p orbitals or s orbitals, simply they are giving pure orbitals. Then what is the ratio? Total how many hybrid orbitals? 18. Total number of pure, 6 plus 6 12. Okay, 6 are 3 are 3 are 2 are 2 is to 1. That is the ratio, 2 is to 1. Ratio between hybrid orbitals and pure orbitals, 18 is to 12. One second, I did mistake, I think. 3 6 are 3 4s are 12. Clear? Next one, 2 2s are 2 3s are. Yeah, this is the right answer. Small mistake, please observe. 18 is to 12. 2 6 are 3 6 are 3 6 are 18. 3 4s are 12. Yes, 2 2s are 2 3s are. This is the answer. Ratio between hybrid orbitals and pure orbitals. Clear? Right. Yeah, next concept, classification of organic compounds. From here also we are getting one question, very important. Classification of organic compounds. Next one, classification of organic compounds. Yeah, classification of organic compounds. Yeah, classification of organic compounds. So actually here organic compounds are classifying like this. Very simple classification, not much lengthy, right? First one, acyclic compounds. Acyclic or open chain. First I am going to write open chain. Open chain. Open chain nothing but cyclic or acyclic. Yeah, acyclic compounds. Next one, closed chain. Closed chain. These are also known as cyclic compounds. Cyclic compounds. Yeah, that is the first basic classification. Our organic compounds are classified into two types, main two types. What is first one? Open chain. How much time completed? 40 minutes. Yeah. Open chain or acyclic. Second one, closed chain or cyclic. Open chain, again two types are there. Yeah. These are saturated saturated hydrocarbons. Saturated hydrocarbons. Second one, unsaturated unsaturated hydrocarbons. Unsaturated hydrocarbons. What are the best examples for saturated hydrocarbons? Saturated hydrocarbons from open chain. Best example for saturated hydrocarbons are alkanes. Okay, alkanes. Next one, unsaturated hydrocarbons are alkenes and alkynes. Alkenes and alkynes. Alkenes and alkynes. Clear? Saturated hydrocarbons are alkanes and unsaturated hydrocarbons are alkenes and alkynes. Next, what about closed system? Now in case of closed system, we have carbocyclic and heterocyclic. Here carbocyclic, second category heterocyclic. Heterocyclic. Yeah, I'm going to give examples for carbocyclic and heterocyclic and what is the difference between carbocyclic and heterocyclic. So once again, so before going to carbocyclic and heterocyclic, how we are classifying organic compounds? Organic compounds are two types, open chain and closed chain. Open chain again two types, saturated hydrocarbons and unsaturated hydrocarbons. What are the best examples for saturated hydrocarbons? Alkanes. And unsaturated hydrocarbons, what are the best examples? Alkenes and alkynes. Okay. Next one, in case of closed chain, what are the two types? Carbocyclic and heterocyclic. What is the meaning of carbocyclic and heterocyclic? Yeah. First I am going to take carbocyclic. Carbocyclic. In carbocyclic, what type of atoms are present? In carbocyclic only carbon atoms are present. Okay, just I am taking like this, carbon carbon, here carbon 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 carbon, whatever the number of carbon atoms you are selecting, right? Now only in the ring system carbon atoms are present. Your ring is formed by only carbon atoms. Now we can write same point. If ring is formed by carbon atoms, only carbon atoms. If ring is formed by carbon atoms, then it is called carbocyclic. Carbocyclic ring. If ring is formed by only carbon atoms, then that ring is said to be carbocyclic ring system. Then what about the heterocyclic ring system? Now come to next one, heterocyclic ring system. Now in case of heterocyclic ring system, now I am taking like this, yes, one second, yeah, heterocyclic ring or heterocyclic rings. Remember this point, in case of heterocyclic ring systems, along with carbon, along with carbon, some elements are present in the ring like nitrogen, oxygen, sulfur, phosphorus and so on, then the ring is called heterocyclic ring. Heterocyclic ring. Heterocyclic ring. Okay, clear. That is the difference between carbocyclic and heterocyclic. What is the difference between carbocyclic and heterocyclic? Carbocyclic nothing but within the ring system only carbon atoms are present. Your ring is formed by only by the combination of carbon atoms. Whatever the ring size 3, 4, 5, 6, 7, 8, 9, 10, whatever it may be, but all the atoms should be carbon atoms, then that is said to be carbocyclic ring system. That is also known as homocyclic ring system. No problem. Next one, heterocyclic ring system. What is the condition in heterocyclic ring system? Along with the carbon, some extra elements are present. Here these atoms are known as heteroatoms. Heteroatoms, and the corresponding ring also known as heterocyclic ring system. Once again come to the same statement. Along with the carbon, some elements are present like some elements present in the ring like nitrogen, oxygen, sulfur, phosphorus and so on. Then the ring is called heterocyclic ring. Okay, right. That is the condition between carbocyclic and heterocyclic. And please concentrate about this point also. Now this is also very important. So once again, carbocyclic two types. Carbocyclic two types. Carbocyclic two types. What are the two types? Now in case of carbocyclic, we can take like this. Now alicyclic, just like one second. Before going to give examples, alicyclics, next one aromatic. Yeah, this one aromatic. Again in aromatic two types are there, right? Benzenide and non-benzenide forms. Benzenide and non-benzenide. Non-benzenide. Here just I am giving examples. Rules and everything we will discuss under general organic chemistry. There is a separate topic for aromaticity. There nearly 2 to 3 hours I will discuss about aromaticity. Here just I am giving the examples. Alicyclic ring system. What are the best examples for alicyclic ring system? Simple 3-membered ring. Next 4-membered ring. 5-membered ring. Cyclopentane. Next one cyclohexane, like that. These are known as alicyclic. Next one benzenide. Best example benzene. Okay. Next one naphthalene. Next one anthracene. These are benzenide aromatic hydrocarbons. Okay, these are the examples for benzenide forms. And non-benzenide, one of the best example is azulene. In case of non-benzenide, best example is azulene. There is a separate story about azulene molecule that we will discuss under aromaticity. One second. Non-benzenide example I am taking like this. Yeah. Yes, 5-membered ring system. Here I am taking pi, alternative positions pi, and pi. What is the name of this molecule? This is known as azulene molecule. Azulene molecule which comes under aromatic compound, but benzenide or non-benzenide. There is no benzene skeleton. That's why it is non-benzenide. Okay, non-benzenide aromatic hydrocarbon. And we can also write another simple example with 7-membered ring system. Yes, double bond O. Next here some pi bonds are what given like this. This is also non-benzenide aromatic compound, right? Carbocyclic ring system two types, alicyclic and aromatic. Again aromatic how many types? Benzenide and non-benzenide. What is the difference between these two? The name itself indicating that benzenide nothing but they are containing benzene rings, Non-benzene and nothing but they are not containing benzene rings. Okay, that is the classification. And come to heterocyclic compounds. Now in case of heterocyclic compounds, just one extra heteroatom is present. Okay, so directly I am going to give examples like this. Now identify heterocyclic compounds. Identify heterocyclic compounds from the following. That is our question. Okay, identify heterocyclic compounds from the following. Now let me give these examples. Yes, outside the ring system, something like oxygen atom is given. Next one here, nitrogen is the part of the ring system. Next one, 5-member ring system, oxygen is part of the ring system. Okay, yes. Next example, same like sulfur. Okay, next one, nitrogen. Yeah, next another simple example, just to identify heterocyclic or not. That's enough. One second. Yeah, these are rough. Identify heterocyclic compounds or not. Yes, you start from first molecule. Now in this one, oxygen atom is outside the ring system or part of the ring system. In the first example, where that oxygen atom is located, inside the ring system or outside the ring system? Outside the ring system. There is no heteroatom inside the ring system. Your ring is formed by only carbon atoms. That's why it is not hetero. That's why simply I am giving, that is not heterocyclic compound. Yeah. Come to next example. Nitrogen is part of the ring system. Yes, heterocyclic compound. Next one here also heterocyclic compound. I am not going to use aromatic or non-aromatic like that. Why? Because here I am not introducing any rules to identify aromatic and non-aromatic, anti-aromatic, homoaromatic, quasi-aromatic, that we will discuss under general organic chemistry. Yeah, it is aromatic, sorry, heterocyclic or not, heterocyclic compound. This one, yeah, heterocyclic compound. Why? Because one heteroatom is part of the ring system. At least one atom is sufficient, right? Yeah. Next one, nitrogen. Yes, nitrogen. Yes, two nitrogen atoms. Minimum one atom is present inside the ring system. Then that compound is said to be heterocyclic compound. Okay, that is the basic classification of organic compounds. Next one, before leaving this class, I am going to give classification of bicyclic compounds. Now this one also very important. You can observe questions from PYQs, only classification, but there is no much chemistry about this bicyclic compounds. Yes, classification of bicyclic compounds. Classification of bicyclic compounds. Okay, in the classification of bicyclic compounds, we have mainly three types. Yeah, first one, fused compounds, fused compounds, fused compounds, fused compounds. Second one, bridged compounds, bridged compounds, and spiro compounds. Spiro compounds. Okay, yeah, fused compounds, bridged compounds, and spiro compounds. Just I am giving examples, and remaining molecules I will discuss under stereochemistry. What are the examples for fused compounds. In case of fused compounds, now two rings, yeah, this is the example for fused compound. For example, six-member ring system is given. In between these two, just they are giving one sigma bond. These two rings are fused together. Right side, what is the ring size? 5. 1, 2, 3, 4, 5. 1, 2, sorry. 4-member ring, left side also 4-member ring. This is one 4-member ring, right side also 4-member ring. These two are what? Fused together. Next, another simple example here. Something like 4-member ring is given and in between these two, sigma bond is there. That is also fused compound. Okay, right. Next one, examples for bridged compound. Now just you look at this one. In case of bridged compound, okay, just I am taking that 6-membered ring system. I am taking one common carbon atom. That common carbon atom is connected to this carbon as well as this carbon atom. Now this carbon atom is considered as bridged carbon. Here how many bridged carbons present? One bridged carbon atom is present, right? Spiro compounds. What is the meaning of spiro compound? For example, for both the rings, left side one ring, right side one ring, and this carbon atom is taken as what? Common carbon atom. Common carbon atom. For both the rings, one common carbon atom is present. These compounds are said to be spiro compounds. Now these are the best examples. Yes, four-membered ring systems. Yes, here it is the common carbon atom. Now for example, we can use one 5-member ring system, one 4-member ring system, no problem, or two 3-membered rings, that is also spiro compound. For example, if you are using like this one 4-membered ring and one 6-membered ring, that is also spiro compound. Just only basic classification, right? Bicyclic compounds in terms of what? Fused compounds, bridged compounds, and spiro compounds. Now these are the fundamentals of organic chemistry. I think in 3 lectures I covered this total fundamentals. In the next lecture we will go for IUPAC nomenclature. Okay, IUPAC nomenclature, and after that we have some topics like optical isomerism, geometrical isomerism, and conformational isomerism. Okay, thank you.